We've talked about offset voltage, we've talked about offset current, and we've talked about bias current. Now let's go and analyse how we can actually select the right op-amp for the right application. And we use a concept called figure of merit. So let's take a simple design example and see how we would actually derive a figure of merit and how we would choose the right op-amp. So in the last example, we had a single number, which was the offset voltage, which dominated the specification. But often many of the different parameters contribute, so how do we choose? So let's try and define a figure of merit. A figure of merit is a function of all the significant contributions to an error that gives a total system error. Figure of merits must change monotonically, in other words, they must continue to increase or decrease with the overall error due to the component variations. So we want to look at the total error contributed by the component, which is clearly a good indication of the correct component choice. So let's go back to our integrate and hold circuit again. And here we have a simple circuit. We've got a switch at the input that either connects to the input voltage, in which case it integrates, or it connects to ground, which means that actually the output voltage is constant. When it integrates, the output voltage changes at the rate of minus the integral of the input voltage divided by the resistor multiplied by the capacitor value. And when S1 is equal to 0, the output voltage is nominally constant. One of the important issues with memory, and capacitive memory in particular, is the concept of memory drift. So when the input voltage is at 0, the output voltage should not change, but due to errors such as offset bias, offset voltage or current, it can actually change and it causes a drift in the output voltage. Looking at our circuit, we have a bias current. We have an equation that defines this, and the change in output voltage with across time is 1 over C multiplied by the bias current plus the offset voltage divided by the resistance. We have a fixed time constant here, tau, which is equal to the product of resistance times capacitance. Effectively, we only really have one free parameter here, which is resistance. And the change in output voltage across time equals 1 over tau times I bias times resistance plus the offset voltage. So looking at this equation here, the optimization would be to make the resistance as small as possible, because that will give us the least error in the output voltage. We can't change the offset voltage because it's a fixed. If we now go and look at the data sheet for a typical amplifier, here we have a variation in the output voltage compared with the load resistance. If R is too small, the input voltage range is too small. So we need to try and optimize the value of R. And it also impacts supply current, power dissipation, and also things like thermal drift, which we're not going to consider here, but those are the things that it might come and impact. It is also impacted by the available values of capacitance. So we're going to choose a resistance of R is greater than or equal to about 2 k ohms. And that gives us a reasonable trade-off of output voltage capability compared with current and also the choice of values. So let's go back to our naive circuit. If we want a tau of about 10 seconds, then for a 2 k ohm R, we require a capacitance of about 4,700 microfarads, or 4.7 millifarads. It's really difficult to get high quality 4,700 microfarad capacitors. So let's change the input resistance from 2 k ohms up to 2 megohms, and also let's change 4,700 microfarads to 4.7 microfarads. So we've increased the value of R, we can reduce the value of C because we're interested in the product of R times C. And now if we crunch our numbers, we can see that we have the product here, which is the change of voltage per time, is equal to 1/10 seconds, which is tau, times the bias current, times the resistance of 2 ohms, plus the offset voltage of 10 millivolts, which gives us about 1 millivolt per second variation in the output voltage. So let's look at how large a 4,700 microfarad capacitor would be. Now you can buy electrolytic capacitors which are relatively small, but they're very low quality. They are not good tolerance. They can be plus 100%, minus 50%, which is quite common. So we've identified a high quality polypropylene capacitor here that would be 4,700 microfarads. And it comes out to this one here. So let's compare that size, a cat. Not a cap, a cat. Okay. And I actually have a 4,700 microfarad cat here with me, which will demonstrate the size and shape of a large capacitor. This is Misty. Say hello, Misty. And that is the size of a 4,700 microfarad capacitor. And if we look at the value here for a medium-sized cat between 4 and 6 kilograms, this is approximately the same size as the capacitor that we need to use for your original circuit. I hope that's given you some insight into roughly how to do the analysis for figure of merit. We will then move on to look at figure of merits in more detail and how you could apply these for other circuits that you may want to do.